The last section of this chapter deals with the number of solutions for a system of linear equations. What we have been doing, we have been finding the solution to a system of linear equations. That, Keen, be quiet. The solution is the point of intersection between two lines. So most of the ones that we've looked at, there was a point of intersection. There was one solution. Now, there are actually two other things that might happen. And probably some of you have already maybe thought about this. If the two lines are parallel, they will never cross, and therefore there would be no solution to that system of equations. But there's also one other thing that could possibly happen. So that's what we're going to be looking at today. What are the different possibilities when you have a system of equations? So we're going to explain why systems of linear equations can have different numbers of solutions. We'll identify how many solutions a system of linear equations has, and then we'll get into solving some problems involving these scenarios. All right? So if we go on to the next page, the first example says, express each of those in slope-intercept form, graph them on the same grid, and then we'll see how many points of intersection there are. So for the first equation, again, we want to get positive y by itself. Probably what I would do here is I would add the 2y to both sides. Okay. Cheney, you with us? Okay, guys, get your packages open so you can copy this down. Page 45 now we're on. And then, then copy it down. Then divide both sides by 2 to get positive y by itself. And it doesn't matter which side it's on. Positive y will equal. The number in front of the x is 1, so that'll be 1/2 x minus 3. That line will have a y-intercept of -3 and a slope of 1/2, so we rise 1 and run 2. Rise 1 and run 2. We can also rise -1 and run -2. Rise -1 and run -2. So there's that first line. And again, we always put arrows on the ends of our lines because they continue forever in both directions. So now we do the same thing for the second equation. 2x minus y plus 3 equals 0. This one's a little bit easier because all you have to do is just add the y to both sides. That'll make positive y by itself on one side, equaling 2x plus 3 on the other side. This line has a y-intercept of 3 and a slope of 2. So you'll rise 2 and run 1. Rise 2 and run 1. You can also rise -2 and run -1. Rise -2 and run -1. All of these will work as well. So not only can we see that there is a point of intersection here, we can also see that it looks like it's at the point -4, -5. We're not actually asked to state the point of intersection, just how many points of intersection there are. And in this case, there is one point of intersection. So we're going to leave that last part until we're done the next two examples. And then we're going to go back and talk about how we can use just equations without actually getting y by itself in order to see how many solutions you have. So for number 2, express each of these in slope-intercept form. So for the first equation, I would subtract the 5x and the 3 from both sides, and then we'll divide both sides by positive 3 to get y by itself. So negative 5/3 x, take away 1 is our equation. That has a y-intercept of negative 1, and our slope is negative 5/3. So how do we do that, Brock? Okay, stay with us, please, okay? Negative 5/3. Rise negative 5, run 3. You can also rise positive 5 and run negative 3. All those points line up, so we can draw our line going through them. So I need to check because I'm off a little bit here. 1, 2, 3, 4, 5. Oh, I only ran negative 2 for that point instead of negative 3. Okay, there we go. So there's that line. What do we do for the second line, Keen?
What next?
10x plus 6y equals 30. What do we do? 10? No, 10x. You're going to subtract 10x from both sides. The 30 is positive, so it stays positive. And then we would divide both sides by 6. Everything gets divided by 6. And that'll give us y equals negative 10 over 6 becomes negative 5 over 3 plus 30 over 6 is positive 5. This line has a y-intercept of plus 5 and a slope also of negative 5/3. So you're going to rise negative 5 and run 3. Rise negative 5 and run 3. These two lines will be parallel lines. They have the same slope. So this is an example where there will be 0 points of intersection. Because they are parallel lines, they have the same slope, they will never cross. So in this case, there are no points of intersection. And again, we're going to save that last piece to the very end. Now, for number 3, again, we need to get both equations in slope-intercept form so we can graph them. For that first equation, I would start by adding the 5y to both sides, and then we would divide everything by 5. So y will equal 2 over 5x plus 2 when you divide everything by 5. So that has a y-intercept of plus 2 and a slope of 2/5. So rise 2, run 5. You can also rise negative 2 and run negative 5. Those 3 points will line up, so we can draw a line through them. With arrows on the ends because our lines continue forever in that direction. Our second line, we would just have to divide everything by 10. It's already got the y term by itself and it's positive. So that'll be y equals 4 over 10, which reduces to 2 over 5x plus 10 into 20 is 2. They are the same equation. When you put them in slope-intercept form, they are the same equation. So they will have the same line. And so when we're talking about how many points of intersection there are, in this case, there are infinite points of intersection. They are, in fact, the same line, so every point is a point of intersection. This is the third scenario. When you look at the equations, they don't look the same, but when you put them in slope-intercept form, you actually get the same equation, which means they are the same line and there are infinitely many solutions. So now we'll go back and answer the part, what do you notice about the equations? So here's what we'll do. For the first set of equations, we'll stack them on top of each other And just make sure the terms are in the same order, which are x, then y, then constant equals 0. Essentially, they're in general form. They're essentially in general form. Okay, so let's go back and do that with the other sets of equations. So for number 2, it's 5x plus 3y plus 3 equals 0. The second equation is 10x plus 6y. Now we have to move the 30 over because we want the terms in the same order. So I subtracted the 30 from both sides to make that happen. And that's those two equations. So again, I'm stacking them on top of each other and putting them in the same order. And then we're going to use this to make a comparison. So the third scenario, again, if we stack them and make sure that the terms are on the same order. So I got the 4x. If I move the 10y over to the right for this second equation, it'll be minus 10y. And then plus 20 equals 0. Now, let's start with this set that we just wrote down. If you look at the terms, the x terms, the y terms, and the constant terms, and you compare them from one equation to the next, what you should notice is that if you take that first equation and you multiply every term by 2, you will get that second equation. 2x times 2 gives you the 4x. Negative 5y times 2 gives you negative 10y. 10 times 2 gives you 20. If you multiply all the terms in the first equation by 2, it exactly gives you the second equation, which means that these two equations are multiples of each other. Every term is the same multiple when you compare the terms. That is the reason why there are infinitely many solutions. When one equation is an exact multiple of the other, when you put them in slope-intercept form, you're going to get the same equation once you simplify it. So in this case here, what do we notice about the equations? They are multiples of each other. Because you can actually do it two ways. You can go from the first equation and multiply it by 2 to get the second equation, or you can start with the second equation and divide by 2, or multiply by a half to get the first. It goes both ways. But all the terms are the same multiple of each other, all the terms. And because of that, they are in fact the same equation. Now, as we back up to the second example, that's partially true, okay? If you multiply the 5x by 2, you will get the 10x. If you multiply the 3y by 2, you will get the 6y. But when you multiply 3 by 2, you don't get negative 30. You get positive 6. This was the example where the equations were parallel. They had the same slope. And for that to occur, what happens is that only the x and y terms are multiples of each other. Right? 5x times 2 gives you 10x. 3y times 2 gives you 6y. It's not the same multiple for the constants. So in this scenario, the x and y terms are multiples of each other. And in the first scenario, when we look at the equations and compare them, you can multiply the x by 2 to get 2x, but when you multiply negative 2y by 2, you get negative 4y. And then you multiply negative 6 by 2, you'll get negative 12, not positive 3. So in this case here, one equation, no parts of one equation are multiples of the other. In other words, either the x and y terms have to be multiples or the entire equations have to be multiples. If neither of those two things happen, then they are two different lines with different slopes. And as soon as you have different slopes, the lines will always cross. So what we could say here is that the x and y terms are not multiples of each other. If they're not, then it doesn't really matter what the constant terms do. So again, the x and y terms are not multiples of each other. Okay, so on the next page, when two lines are graphed on the same grid, they do not always have exactly one point of intersection. Parallel lines do not intersect, so there's no solution. Coincident lines are lines that occupy the same position. They have an infinite number of solutions because the lines are equivalent. They overlap. So again, a system of linear equations can have one solution, no solution, or an infinite number of solutions. Before solving, you can predict the number of solutions for a linear system by comparing the slopes and y-intercepts, right? You'll have one solution if they have different slopes. And it doesn't matter what the y-intercepts are. If the slopes are different, then you will have one solution. And that occurs, you remember, when the x and y terms are not multiples of each other. There's no solution when they have the same slope but different y-intercepts. Two different lines with the same slope. And that occurs when the x and y terms are multiples of each other. The third possibility is when you have the same slope, same y-intercept. That's when one equation is a multiple of the other. So in these examples, it says how many solutions does each have? Justify your answers. So we now have two choices, right? We can get both equation and slope-intercept form, and you actually don't even have to graph them. Compare the slopes and compare the y-intercepts. So that's one way to do it. So let's do that for this first example. I'll leave the negative 2y on the left for now. I'll subtract the 3x and keep the positive 9 over there. And then when you divide both sides by negative 2, negative 3 over negative 2 is positive 3 halves x. 9 divided by negative 2 is minus 4.5. So that's the first equation in slope-intercept form. For the second equation, if you just divide everything by 4, because the way that equation is written, the 4y is by itself already. So now if you just divide everything by 4, you're going to get y equals 3 over 2x minus 18 divided by 4 is 9 over 2, which again is 4.5. So these two lines are in fact the same. Therefore, there are infinite solutions. Now, we also could have done that by writing the two equations so the terms are in the same order and comparing them. So I'm going to keep this top equation as is. I'm going to rewrite the bottom equation above, but having the terms in the same order as that first equation. So the 6x comes first, then the y term. You bring the y term over here by subtracting 4y from both sides. And the 18 is brought to the right by adding 18 to both sides. And when you compare these two equations, you can see if you multiply the first equation by 2, it gives you the second equation. That's another way we know that they are the same equation. If you multiply this equation by 2, it will give you that equation. So let's use that method for question B. These are in the same order. You've got x, then y, then constant equals 0. The bottom is x, then y, then constant equals 0. These equations are not multiples of each other. And the x and y terms are not multiples of each other either. Okay? So in this case here, they are two different equations. So therefore, there is one solution. So we can say the two equations are not multiples of each other. And more specifically, as we saw earlier, really, it's important that the x and y are not multiples of each other. That's really what tells us that they are two different lines. They'll have different slopes, so therefore there will be one solution. So this is certainly easier than actually solving, than actually putting both equations in slope-intercept form to see what the slopes and y-intercepts are. If all you're asked for is how many solutions are there, this is all you have to do. Okay? So for question C, I'm going to put the top equation in the same order as the bottom equation, which means I've got the 3x first by itself equals, I'll move this minus y over to the right by adding y to both sides, and then the positive 4 stays on the right as well. So it doesn't move, so it stays positive 4. When we compare these together, if you multiply the bottom equation by 2, just the x term, 3x times 2 gives you 6x. And the y times 2 gives you 2y. The 4 times 2 gives you 8, not 10. The x and y terms are multiples of each other. That means that these two lines have the same slope, different y-intercepts. They're parallel lines, no solutions. The x and y terms are multiples. So therefore, they will have the same slope, but different y-intercepts. So therefore, they are parallel lines, and there's no solution. They will not cross because they are two different lines that are parallel. Okay? We're going to stop there for today. And you can work on those questions. I will post the solutions to Google Classroom so you can check your answers. There's still a bunch of you that haven't handed in that one assignment that was taken in for marks in this chapter. Okay, it's on Google Classroom. It's also on PowerSchool now because I've marked the ones that were handed in. I want to say it was maybe page 428 and 430. Okay? So you got to make sure you get those done and handed in. Page 428 and 430.